Hi everyone, welcome to of Mach Ports and XPC. This is going to be a talk about interprocess communication on iOS. And my name is Omer. This is my Twitter handle at AllInHead. And let's dig right in. So just before we go to our main topic, just a little more about me. So I work in this company called Garena, and it's part of a larger company called C. So we are an internet company in Southeast Asia, and we're expanding throughout the world right now. Garena, the platform I work with, is a game publishing company, um, and basically we're a fun company, not very big yet. This is a photo from our Christmas party last year. We're based. Our main office is in Singapore, and this is in the era before COVID-19 became rampant. So that's why there's no social distancing here. God, that feels like a long time ago, right? If I zoom in on myself here, so that's me. Yeah, enough said, right? Okay, so let's dig right into our topic. Okay, so talking about partying, right? Let's actually revisit the '90s. I'm sure lots of you guys love the '90s. A really nice time, good music, disco. A lot of people are nostalgic about the '90s, right? Those good old days. So, but if you think of it from a software point of view, and you remember the early '90s, especially, where Apple used to have this fancy logo at that time. But at that time, especially in the early '90s, what was going on was the age of the PC was really beginning, like proper. So PCs were revolutionizing everything, right? And Windows in particular was rapidly gaining market share throughout the world. And Apple at that time is in a bit of a trouble because they're still trying to find out what's the best way to get in and into this market properly. Like what's they're still figuring out their strategy, and one of the things is at that time Apple was being led by that ex Coca-Cola CEO. I forgot his name. Steve Jobs is not in the picture, so the company culture is not the kind of product focused company that we know today. So at that time, they did what they thought they should do to respond, and they launched these new Macintosh lines called Quadra, Centris, and Performa. The very fact that you probably never heard of these kind of is indicative, right? They didn't really work out. So I have never heard of them before either. Before I researched this a bit. So what? So what? So this time Apple's not doing well, but then something changed, right? And that's the reason why that's important to this talk, and the reason why we're covering this history is because everything changed after that. And what happened was Apple acquired NextStep. So NextStep is this other company that was founded by Steve Jobs after he quit Apple, and or after he was fired by Apple. And NextStep is quite interesting. They were doing some fascinating work in terms of software. So so what happened after the NextStep acquisition is the macOS Classic, the pre-NextStep macOS. I mean, it was totally destroyed. I mean, nothing remained from there. They kind of redid everything. And NextStep provided everything from the foundation. This is the same NS foundation that we know and love today, to the kernel. Everything was provided by NextStep. And the genetic pool of NextStep is still visible today. So it's been a long time since then, 20, 30 years, 20 plus years, but almost 30 years, sorry. But there are several genetic artifacts that are still very visible today, even though it's been that long. So things like the NS prefix, NS standing for NextStep. So if you use NS array, NS mutable array, NS dictionary, etc. Especially those guys who use Objective C, which is totally fine, by the way. Objective-C is a perfectly good language. Use the best tool for the job. If speaking of Objective-C itself actually was developed by Next Step folk. The Mach binary format, which is ubiquitous in the Apple ecosystem today, as well as Mach ports, which is something that we're going to talk about in more detail now. So all this stuff basically came out after the Next Step acquisition, and this kind of transformation of Apple into this product focused company was kind of happening, and this Next Step invasion at the software layer was kind of part of that, right? So they redid everything and they made it better, right? So a lot of this stuff, the fact that a lot of this stuff is still in place today and is still performing the same functions is kind of evidence of the fact that this thing worked well. Many of these decisions that I made then worked well. So before we jump into IPC proper, we need to take a little OS class just to contextualize things a bit better, and if you want to compare IPC on macOS and iOS, etc., with other operating systems, it's a good idea to understand the differences between a monolithic versus a microkernel design. So very briefly, so a monolithic kernel is this architecture for an operating system where the kernel is basically doing everything. So on the application side, when you make a system call, from that point onwards, everything is handled by the kernel. So the kernel will, so let's say you're doing, some network request, right? So you're sending some data over some socket, because that's the system call that you're going to call, the send system call, for example. What's going to happen under the hood is the kernel will talk to some device drivers. It has an implementation of the networking stack, all the OSI layers, like the different networking protocols. All that is implemented at the kernel layer itself, and the kernel will talk to the relevant device drivers, copy over the data to the device hardware, and do all this magic. But all this is handled by the kernel. So the nice thing here is performance, because there's no layers of abstraction, so it's as fast as it can be, right? There's no added code that needs to execute or not. So this part is quite nice. From a performance point of view, this design makes sense, and one of the reasons why most operating systems are kind of monolithic kernel based is primarily to performance. So that's in contrast to a microkernel based architecture, where the idea is that instead of the kernel taking up so much responsibility, we can split the responsibility up into several key components. So let's say you can have a device driver component which is running at the same level as any other application process. So all these are running as separate processes, and then what we do is we have a good IPC mechanism that talks to these different processes, kind of like microservice architecture, if you guys are familiar with that in the server space. So each of these are small services, and our applications can talk to these services, and all the kernel is doing is just providing that IPC mechanism, doing some virtual memory, some scheduling, but it's very bare bones. It doesn't do as many things. And the nice thing about this design is that you get more stability, because let's say you have a bug in your device driver which suddenly causes the driver to crash. It will not take your kernel down, so you won't have a blue screen of death if that ever happens. Similarly, from a security point of view, this is better, right? Because there's fewer chances that bugs will lead to security vulnerabilities, basically, because your kernel is much smaller. So in theory, this sounds like a pretty nice design, as long as you can handle the performance problem, and that's so normally that's not an easy problem to solve. So normally most modern operating systems will do a trade-off between these two designs. So and macOS and iOS and cousins, watchOS, tvOS, I'm just going to call all of them StarOS, Are they monolithic or micro? Well, they're actually neither in the classic sense. They're a bit of both. Um, uh, if you look at the kernel itself, so XNU, which stands for X is not Unix, this is the kernel that powers all these operating systems. It's macOS, iOS, tvOS, watchOS. The nice thing about this kernel is actually this kernel is open source. So you can actually read the source code for this kernel. Quite interesting. XNU has a very fascinating backstory. So XNU is primarily based on this project that was done in Berkeley called Mach, which is a microkernel. So Mach provides some very fundamental microkernel things that if you are building an operating system with a microkernel, it's a good place to start. The problem with Mach is that you can't build a full-fledged operating system just by Mach, because Mach is by definition, as I explained earlier, is a microkernel, so it doesn't really do a lot of things by itself. So what these guys did with XNU was they use FreeBSD, which at that time was a good open source operating system implementation. They use FreeBSD as kind of a upper layer over the Mach lower layer, sort of. So in that sense, XNU suffers from a bipolar personality disorder because it has these traditional Unix style system calls, like the thing we were discussing earlier, the send, and many other Unix system calls. Those all will work correctly, but it also exhibits this Mach layer, which is kind of unique. So and you can see both APIs. So it's quite interesting that it has support for both of these. So it's not so if I was to answer, is it a microkernel or a monolithic kernel? It's kind of a mixture of both, but it's a bit more microkernel-y in some ways, and we'll get to that why, especially with XPC later on. Okay. So we talked a lot about we set up the context, right? So we have this thing called Mach, which is providing us some IPC mechanism. So let's look at that IPC mechanism itself and see what that looks like. And Mach IPC is actually based on this concept of ports. So a port is basically just a number. It's like an address, or it's like a post box. So you can basically send and receive messages to ports, and you can use this API called Mach ports allocate. If you want to allocate a new port, this will help. This will cause the OS to give you a new post box, so to speak. And messages are going to be sent and received to a port. So let's say you create a new port, then you can receive messages from that port, for example, or you create a new port and you can decide to send messages to that port. But you need somebody to specify this, right? What are you using this port for? And that brings us on to the discussion about ports rights. So when you have a port, you have associated rights with that port. So when you as a port user, you can have a send right to that port, meaning that you can send things to that port, send messages to that port basically. Or you might have a receive right, which means you can receive messages from that port. So one of the things that is interesting about these port rights is, so aside from send and receive, you also have some other interesting rights like send once, which is quite useful in a OS setting, because a lot of the times, a lot of system calls you make are going to be like one time and then you don't need it anymore, right? So this is a pretty efficient kind of business logic layer, basically, that'll help guarantee that this thing only happens once. One of the interesting things about port rights is the number of things that can hold that port right. So for send and send once, for example, there's no such limitation. You can have 0 or many port right holders, and that makes sense, right? So basically, let's say imagine that you have a shared service, and a lot of people are able to send messages to that shared service. So sending is not restricted, but if you think so, but for receiving from a port, only one user of that port is able to use that port receive message from the port at any given point in time, and that makes sense, right? So think about with the postbox analogy. Many different people can put letters inside your postbox, but only you have the key to unlock and extract out the messages from inside there, right? So that's the key idea over here. Moving on. So one of the interesting things about ports is actually the port rights can be passed around in messages, which is interesting. It leads to some very interesting use cases. We're not going to go into too much detail right now. We just want to let you guys know about this. So the question about ports, and we talk about addresses. So ports are like addresses, right? So you need some registry, right, to look up to know if you want to send a message to someone. How do you know what their address is or what their port number is? And for that, you need some kind of central service, right? So Mach requires a central service where users here being applications or other processes, whatever, can discover each other and they're able to send messages. So these days in StarOS, this role is provided by a service called LaunchD. So LaunchD is something that all services will register themselves with, and LaunchD knows what's the port number of each of these services, basically. Okay, and let's just look a bit at the message format for Mach, just to understand a bit more detail. So here is the format, and the way this works is this chunk is basically 4 bytes. So the first 4 bytes will be a bunch of bits that indicate flags. So the flags will include things like the port rights associated with that message. It's going to be a size. Just everything in orange basically is the header. So there's a port number that you're sending message to, the local port for the other person to send your reply to. This probably looks very similar to any other networking packet structure you guys might have seen. Very standard stuff. There's a voucher port thing. I'm not going to discuss this in detail right now. And there's a message ID, and then there's a body. The body depends on the context, depends on what's the procedure call that you are making. And so the arguments to, let's say you're calling a function, you're using IPC to do a remote procedure call, for example. Then the arguments will be inside this body. Yeah. So one of the interesting things about this is how do we serialize the body, right? So how's that formatted? And I'll leave you to think about that. But before we think about that, let's do a quick demo and look at this in action. So just want to show you guys that this is not out of the blue, or this is not theoretical. So what we're going to do now is we're actually going to see how Mach is working under the hood. Okay, so Mach message is the API that is used by Mach when you want to send a message. Okay, so here you can see my Xcode, and hopefully this is clear. So here we have Mach message API. So this is used to send or receive a Mach message. You can ignore most of the arguments. So the interesting argument is that the first argument is a pointer to the message header. I'll just keep that in mind. The message header is exactly what I showed you guys earlier. This is orange bits. This is the message header. Okay, just keep that in mind. So what we're gonna do is we're gonna add a symbolic breakpoint to the Mach message. Okay, and the reason we want to do that is we want to see what kind of Mach messages are being sent when you launch an app, for example, or when you do anything. Just for us to explore and see what's going on when we normally run an application. What's Apple doing under the hood? What the framework's doing under the hood? So let's quickly run this, and let's see where the breakpoint triggers. Right. So we're running this. So this is here is a Mac app. The reason I'm using Mac app is because it's a bit easier to. We can do this on iOS too. But some of the headers are for some of the things that we're going to do later on. They're more publicly available on Mac, so as opposed to iOS. That's why it's just a bit easier. But the basic idea remains the same. Okay, so so we have our first stack trace here, and this is quite interesting. This is interesting because if you guys look at this part, you can see that this is actually called and DYL. So this is actually called as part of library initialization. So what's going on here? So basically, before your main is called, so every app has a main, right? But even before the main is called, there's actually this program called DYL. There's actually this thing called DYLD that's actually going to prepare all your libraries that you are linked with, and it's going to initialize all those libraries before calling your main. And what's happening here is, so DYLD is doing its stuff, and one of the libraries that usually most applications have is pthreads. So pthread init basically will call this function called host info. So host info is this OS system call that basically gives you some information about the system that you're running on, and we can see that's called in pthread init, right? And what's host info is doing is, host info actually is doing a call, is doing a mock message. So host info is, let's just look at host info's definition just to understand what host info is doing. So host info, sorry, not this one. Host info. There we go. Okay, so here is host info, for example. So this is the function call for host info, and what this host info function does is it'll basically send a mock message, and it'll give you some information about the system that you're running on. So you can get lots of interesting information from here, things like the number of processors, CPU usage, memory size, etc., etc. Okay, and what we can see is that it's sending a mock message here. And remember last time we discussed, I showed you guys mock message earlier, right? Mock message, the first argument for mock message is a pointer to the header. So what we're going to do is we can actually read, and let's start to look at what's inside the header contents, and then we try to match them back to our definition and see what's the port number, what's the flags for this message, just to get an idea what's going on, right? So we can do that. So let's do a mem read and $1. So what this will do is it'll take the first argument, the address of the first argument, and it'll read the memory at that address. And oh, sorry, it's $arg1. Yeah. And here we can see, so we get the bytes here, right? So these are the bytes. So this basically corresponds to our message. And what I'm going to do is I'm going to go back to the slides where I've actually parsed this for you guys. You don't have to parse it mentally. So this is the host info thing we talked about earlier. So basically it's the host info function. And here we can see the same stack trace that I showed you guys earlier. So it's basically called as part of host info will call the mock message, and we can do this. So here's the bytes again that I showed you guys earlier. And if you look at, we just took those bytes and put them in our message format. So this is what we get. So we have the message bits, the flags. We have these flags set. The port number is this thing 0305. Actually, this means 503 because this is a little endian. So the local port is 603, and this is the message ID. So if you look at the flags in particular, so what you'll notice is this, we're actually using two flags here. One of the flag is we're using the send once. So the message type here is the send once. The port right here is send once, which makes sense because it's one of those APIs that you're just gonna call once, right? You don't need a long-lived connection, so to speak, here. And copy send basically means you're going to pass this right along. I'm not going to dig into too much detail for this one because we're short on time. Okay, yeah. So just before we go a bit deeper, I just want to show you guys, this is obviously not the only mock message. There's actually a ton of mock messages always being sent. So what I'm going to do is just make this breakpoint run, and let's try to see what other APIs are being called. And you can see that, so there's another one, get clock service. So this is called as part of, some other libc initialization. Probably need to do something with time. And you can see this also is send a mock message. Semaphore create also send a mock message, etc., etc. So There's going to be a lot. There's going to be a lot. See, all these APIs in all part of initialization, even we haven't even started the app yet, and there's so many Mach messages going on. So what I want to indicate to you guys is that Mach message is a very fundamental part of the OS and of the platform. So it's the fundamental way through which a lot of these low-level components are interacting, and this is something that's happening inside your apps all the time. Okay, so this is just so you guys can understand your apps better, right? This is something that's always happening. So your process is going to be sending lots of Mach messages all the time. Okay, and we saw some XPC stuff, right? So we're going to deal with XPC later, but basically you can see that XPC is also using Mach. More on that later on. Okay, so let's go a bit deeper now. And for Mach, as we discussed earlier, we have this thing called the message body, right? So the message body, we need to think about how do we know what's the format of the message body, because that's kind of up to depends on the on the server, right? The person who's receiving the message. So like other RPC solutions, usually what happens is usually code like this, so where you serialize some bytes and you deserialize some bytes. Usually we generate code like this because code like this is quite easy to write. So and usually you use error prone to do this by hand. So a good solution normally here is to generate code. So if you guys are familiar with things like protobuf, for example, the idea here is quite similar. So the idea here is that we want to have some way where we can generate code, and Mach provides this. So Apple has this tool called MIG, Mach Interface Generation, and this thing will basically generate the code that you need to wire up and send Mach messages. And the way you do this is you will have some definition. So you'll have some definition of what you want the message to look like. In this case, for example, we define a routine. So routine, kind of like a RPC call. And what this is the routine name. We specify the task. We specify some arguments. And what this port definition will do is it'll make to generate some code for this. And the way you can test this out yourself if you're interested is you can write a routine, call MIG on it, and MIG will generate some header file. The header file will be shared for any users that want to use this generated interface. There'll be a port server, C implementation, which basically is the implementation code, all the serialization, deserialization code for a server that's providing this service, and then also one for the client, which is the user. Okay. And if you look at the interface, the generated interface, this is what it will look like. So in this case, for example, we were looking at this API called Mach port names. This is a simple API that will just basically list out all the Mach ports that are available to a particular process. Under the hood, it's going to send some Mach messages, and it's going to do a lot of serialization, deserialization work under the hood. But all that code is basically generated. Okay. Yeah. So I think so. I'm going to stop with Mach. Stop talking a bit about Mach. But the reason for that is because Mach is actually quite low level, and for most modern day services, normally we don't use Mach directly. Although it's actually the thing that's powering a lot of things under the hood. Normally we use a higher layer of abstraction. So this higher layer of abstraction is these days is called XPC. So XPC is a much higher level and frankly nicer IPC API, and the idea behind XPC is it's quite a beautiful idea. It's kind of inspired by the microkernel design. So the big idea here is that imagine instead of you writing your application as a monolithic application, you split your application up into several components, and you basically can use XPC to talk in between those components. And those XPC services basically are kind of similar to Unix daemons in the sense that they'll be managed and initialized by the system, and if they're killed, they'll be regenerated, etc. So the architecture generally will be you split the application functionality into self-contained isolated components that use XPC. And the nice thing about this design, same thing with microkernel design, is you get stability, you get security. It's quite a nice design. And this is something that so basically almost all of Apple frameworks will do this. Okay, so UI kit, photo kit, whatever, all these, usually the way they work is the API that you're calling, let's say you're calling photo kit or you're calling UI kit APIs, all they're doing is they're just gonna have some client code on some client library code, so that'll basically generate some XPC call, but most of the actual logic will be implemented in this daemon that's running in the system. For example, for photos, this daemon will be called photod. So normally when you use photokit, you do a query, right, to get the user's photos. The way that'll work is it'll basically fire up XPC's query, XPC call, and that call will send a query to photosd, and photosd will do its magic and then send the response back. Okay, that's usually the idea behind XPC. So as I mentioned, you get process. So the nice thing about this is you get stability. So if one thread has some problem, it won't bring the entire process down. And each of these components are separate processes. So you get a bit more stability. Another related but very strong feature that you get is privileged separation. So that means, let's say you have something that's a bit more sensitive, some service that's sensitive, and you only want to give access to the service to a limited number of people who only have that permission, right? So you can manage this. So XPC provides support for entitlements. So if you don't have a particular entitlement, then you can't access that XPC service. And this helps get rid of a whole wide range of bugs or vulnerabilities, basically. So it's quite neat. Here's a simple example. So Safari, for example, right? Mobile Safari, which is a process that's actually running Safari. It has these two XPC services. These are, maybe you can have many others, but let's just focus on these two. So what's going to happen is there's this XPC service that's doing all the social login stuff, for example. So every time you do a social login thing in Safari, it'll basically talk to this XPC service. The XPC services normally follow the same bundle ID conventions that we follow in our apps. So similarly, it has other XPC service for web content, for example. So it'll talk to. So there'll be lots of communication happening in between these two XPC services. Okay. And if you are curious and you want to find out what kind of data types are supported by XPC, so one of the interesting things sadly about XPC is that it's closed source. So there are some public interface definitions, but I mean the implementation is closed source. But what you could do is you could do a bit of reverse engineering. So if you are curious and you want to find out what kind of data types XPC supports, you can actually run some. So in this case, I'm using JTool. You can use OTool also. You can basically look at the symbols inside this library and do some filtering, basically. So what I'm doing is I'm looking for the data type definitions inside and trying to filter out those that are prefixed with XPC type, because that's what they're called in the code. And we can see that XPC supports, it's quite a rich list. This list is actually very long. I cut it by 2/3 just to make it fit in this slide. But there's a lot of rich data types. So you have your standard guys, the arrays, dictionaries, errors, Boolean, dates, etc. But you also have a lot of other interesting things. They have a shared memory type. And I believe this one is quite interesting because this can be used. I believe this is used for things like iOS services, which is one way how XPC will pass around pixel buffers, right? Because you don't want to copy those all the time. But usually in most scenarios, most applications will end up using dictionaries or arrays, these more kind of serializable types. It's interesting. Another thing about XPC is this, so no one really knows what it stands for, but I think one of the theories is XML, process communication, or whatever. Yeah. Anyways, so here's so the thing about using XPC is the nice thing about so Apple does have some documentation, especially if you are running on Mac, if you're building a Mac app, because they do recommend this architecture for the Mac apps. So here's I got this from Apple documentation, basically, and we can see here that here is an app, and the way you work with XPC is that you create this thing called an NSXPC connection, and you can then send messages and to the service, basically. And you can have, if you want to send message to the service, you follow this protocol. If you receive messages from the service, this protocol. I'll give a demo and this will be clearer then. Okay. One of the things I want to highlight here is, so there's the flow in which how this works. So basically, when you want to start an XPC connection, the way it works is you basically can start a connection, but if you know the service name, which is in the bundle ID I showed you guys earlier, you can basically create, then add an interface to it, basically to proxy the method calls, and you call resume. And basically what this will do is, you will, under the hood, this thing will connect to LaunchD, which we talked about earlier. So LaunchD knows all the XPC services that are available, and then the service itself will have some listener object that's actually listening for new connections, and there's some stuff that we need to do, and basically this thing will be ready to be used. That's the rough flow. Let me show a quick demo of XPC. This is going to be a very, very simple demo. Yeah, so I'm back here, right? I'm gonna let this breakpoint go, and what we're gonna do is just gonna look at some code. So in this project, what I did was I have a very simple app, and in this app I want to use XPC to do something. So in my app delegate, right, let me show you guys. I have a XPC connection, right? So I put everything in my app delegate because I'm a very good engineer. Haha. And what I'm going to do is, so I'm going to create a XPC connection with my service, and this XPC connection conforms to this protocol. So that means the service implements this protocol for me. Here's what the protocol looks like. Very, very simple. It's just going to uppercase my string because I totally need an XPC service for that, right? There's a callback block where it can return the reply. So the way we use this thing is we specify the remote object interface this way, and we need to call connection resume, and then after that we can use this thing. So we call the remote object proxy, which conforms to this protocol, and then we can call the uppercase string with reply, etc., etc. Okay, and this thing will give us the uppercase string, and you can see in the log here. You can see that it works, right? So if you look at the XPC service itself, so here's the XPC service. So very simple. So it's just an object that conforms to this protocol. So this part is very simple. It's just implementing this protocol. So just converting the string to uppercase and returning it in the callback. If you look at the main.m, so what we're doing here is we are in our main function, we are creating a service delegate and a listener, assigning the delegate to the listener, and calling some methods. Basically, we need to do this boilerplate. And what we're doing here is, when this delegate method is called, we will specify the protocol and resume this. So basically, this will be called whenever there's a new connection, basically. So for this new connection, we will every time we have a new connection, we'll create this hello XPC object, which will basically kind of respond to that connection request, and just resume and so on. Okay, so it's quite simple. Relatively, this part is relatively well documented. You can see, you can go to the header, for example, and you can see there's a fair bit of documentation here. So I'm let you guys explore this with yourself. Okay, so so that's XPC, and XPC is used very, very heavily in iOS everywhere. So a lot of frameworks will use it. I don't have time to go through a exhaustive demos on how different services are using it, but you guys can put some breakpoints, like symbolic breakpoints, and try it out for yourself, and you'll be surprised. Okay, I think that leaves us just enough time for some questions. So if there's some questions, please feel free to ask me.